So, the goals of the systems working group are really about improving integration between different softwares that have in the past mostly been really very different. And I see this integration that is necessary in 3 different areas. Integration between systems engineering and design and analysis. If you look at the current status, it's really 2 completely different classes of software that don't talk to one another. And even within the companies where systems engineering is used, the engineers don't talk much to one another either. The second, which is very much also in the title, is really the integration between system and component level analysis and design. So anything that's 0D, 1D, and 3D. And out of that, I would really sector out even the integration between software controls and system hardware design. I sometimes have up a slide which shows the increase in system complexity over time. Almost all of that is due to software. I think last year, cars broke the limit of having more than 100 million lines of code in the car. And that's really the crucial thing. Another interesting number that I learned yesterday, actually at a model-based enterprise meeting in DC, is about Boeing. This is also really about system and subsystem integration. Boeing thought they would make money after selling 125 Boeing 787s. They, at the beginning of this year, sold the 525th and are making the first dollar on that aircraft. And I think they've been flying for I don't know how many years. I've been sitting in them for actually quite some time. And this is really, in that case, was an issue about system and subsystem integration and the way the extended enterprise works. So what do we want to do with a group? We want to explore these integration methods and the benefits and also teach them. We want to incorporate the things that Keith just talked about. So incorporate verification, validation, and accreditation of simulation components and uncertainty quantification. So we want to move towards libraries of accredited component and really increase general awareness of the issue. I'll start with a motivating example that we just worked with, completely anonymously. And this is an example of multiscale coupling multi-body simulations and CFD. And there's people that actually translate CFD as colors for directors because it's not always clear that you really get the value out of it that you think. CFD is used in automotive to compute aerodynamic drag, which you need for fuel economy or range for electric cars. Multi-body you typically use to look at handling, safety, noise, vibration, hardness, all these kind of things. In the past, these 2 things have always been done separately and never been combined. And for a long time, a very significant error in aerodynamic drag has been completely neglected because people couldn't really measure it. Most wind tunnels measure the drag by putting the chassis, they bolt it fast, it doesn't move. There are a few wind tunnels that actually allow it to be measured in a way that you bolt the tires so that the suspension moves freely from the aerodynamic forces. But there is no wind tunnel in the world where you can switch between these 2 measurement methods, which is one reason why people never discovered that they actually had a big error. So the error actually, when people looked at it, was 1 order of magnitude larger than they thought it was, because it wasn't integrated. Quite interesting. And so what happened, that we did a project which enabled the coupling. It was based on a relatively recent standard called FMI, or it's a functional mockup interface between the system-level tool that does the multi-body part and the CFD tool. And the error got much smaller, and it was validated actually against real measurement data for a prototype vehicle in the wind tunnel that allows to actually measure it in the right way with the integration. I think the point that I want to make here is in particular that this integration was based on a standard, and the standard made it, I don't know how much easier in terms of cost and time, because both sides knew exactly what they were talking about. There's open source software to help implement the standard, everything around it. So basically, this multi-scale coupling can do a lot of good, and is one of the goals. And I think there's actually plenty more examples where there's still fairly large errors in terms of how well we can predict stuff with simulations based on not integrating different things which actually influence one another. So what are the issues here? A big issue is silos, as I talked about them. The system level people don't talk to the component level people, even within the same company. The systems engineering people don't talk to the simulation analysis people. The people that do software don't talk to the people that do hardware. The people that do hardware don't talk to the people that do controls. I mean, I'm basically a mechanical engineer that did a controls background, and I know that. It's usually really thrown across the fence, and then people have to somehow deal with it. There's very little talking. Another issue is really lack of funding and momentum for standardization efforts. Interestingly, Boeing is stepping up big time on doing that. They have many people that work full-time on supporting standards exactly because of that. They need them to support the better integration. And there's also a lot of lack of understanding. So there's not so much customer pressure on vendors to do this integration better. So what are the recommendations that we have come up with in past work so far? It's really about develop and evolve existing standards. And there is a lot to it. There's many standards around. Some of them work, some of them don't work so well. I think STEP and STEP-related standards are a relatively important group. Some of them can be really quite very complex. I think STEP on the CAD side took around 15 years, order of magnitude, to get right so that it really worked. And there's still many more standards that are. And there's a trade-off. If a standard is too complex, it won't be implemented, or not be implemented correctly, or it will take 15 years. One standard, the standard that I just referred to with FMI, I think it was successful because it was very simple. It is 70 pages and not 700 pages. And that made it easy to actually implement and apply. And it's used very large for integration between software and hardware development. So yeah, we need to develop new standards where they are missing and promote standards adoption and compliance. Another thing that the FMI people got right was compliance, in the sense that there are tests and end users can look at these tests, they're all published, and see how well the standard actually works. Another recommendation is to develop and evolve best practices and also develop components and component models. We coordinate our efforts with INCOSI and NAFEMS, and I think that is really something which makes a lot of sense here. INCOSI and NAFEMS have a joint working group called the System Modeling and Simulation Working Group, which is a group that connects a lot of end users that are consumers of the technologies, but also vendors, and brings together basically a discussion forum in trying to move these things forward, as well as our friends from SimData. So what are the next steps? We are going to do an assess research paper and to increase understanding why it's difficult, how to move forward, and what to do there. We are starting with a classification of engineering simulation models. I think it was very interesting for me, things that I learned the last 2 days at the Model-Based Enterprise Summit from NIST, how much the aerospace industry is actually really feeling the pain and trying to drive this forward. Because they, in particular commercial airspace, you know, the military aircraft, they don't have the same cost pressures as commercial aircraft. So the commercial side really needs needs to work this hardest.